Section 6.2, the pigeonhole principle. Theorem 1. If k is a positive integer and k plus 1 and more objects are placed into k boxes, then there is at least one box containing two or more of the objects. This is obvious because we can start placing one object in a box until we fill out the k boxes, each with one element, and then the next element must be placed in some box, so that box will have at least two objects. Corollary: a function f from a set of k plus 1 or more elements to a set with k elements is not one-to-one. Here, the second set is the set of boxes, and we have more objects than boxes, so there will be two different objects that will be sent to the same box by the function. Example 3. Among any group of 367 people, there must be at least two with the same birthday, because there are only 366 possible birthdays. So the birthdays are the boxes here, and the people are the objects. Problem 4. Show that if there are 30 students in a class, then at least two have last names that begin with the same letter. There are 26 letters, so the boxes are labeled with them, and there are 30 objects. These are the students. More objects than boxes, so the pigeonhole principle applies. Problem 5. Let n be a positive integer. Show that in any set of n consecutive integers, there is exactly one divisible by n. Solution. Here we cannot apply directly the pigeonhole principle, but we can argue this way. Let k be the first integer, then the set of n consecutive integers is this S. It contains k, k plus 1, k plus 2, and so on, k plus n minus 1, because we start by adding 0, then 1. So the nth integer, to get the nth integer, we have to add n minus 1. Assume that k plus I is less than k plus j, and that they have the same remainder when divided by n. Then their difference, k plus j minus k plus I, is just j minus I, and it must be divisible by n, because they have the same remainder. This is impossible because j minus I is positive and strictly less than n minus 1. I and j are different numbers from 0 to n minus 1, and j is bigger than I. So the remainders are different, and we have a function from S to the set of all possible remainders, which is this set, and this function is one-to-one. F of x is just x mod n. That is the remainder of the integer x when it is divided by n. Since the cardinality of S is n, and the cardinality of the codomain is n, F must be on 2, which means that F is a bijection, and then exactly one element, exactly one number from S will be mapped to 0, so exactly one number is divisible by n. Problem 7. Let the triple xi, yy, zy for I from 1 to 9 be a set of 9 distinct points. So these are the coordinates of the points, and they have integer coefficients. The points are in the x, y, z space. Show that the midpoint of at least one pair of points has integer coordinates. If we select these 2 points, xi, yi, zi, and xj, yj, zj, their midpoint has these coordinates. The average of xi and xj, the average of yy, yj, and the average of zi, zj. These averages are integers if and only if xi and xj have the same parity, that is the same remainder when divided by 2, and the same for the y coordinates and the z coordinates of the points. Now consider these points. This will be the boxes. We have how many? Each coordinate has 2 possible values, 0 or 1. So we have 2 cubed 8 points here. So we have 8 boxes, and the objects are the given 9 points. And we place a point in a box using this rule. X I is reduced mod 2, yi is reduced mod 2, and zi is reduced mod 2 to get the corresponding box. Since we have more objects than boxes, there is a class that is a box with 2 points. This means that the midpoint of these 2 points has integer coordinates. Theorem, the generalized pigeonhole principle. If n objects are placed into k boxes, then there is a box containing at least the ceiling of n divided by k objects. Proof. We'll use a proof by contraposition. Suppose that none of the boxes contains more than the ceiling of n divided by k minus 1 objects. Then the total number of objects is at most k times this difference. But this product is less than k times n divided by k plus 1 minus 1 because n divided by k, the ceiling of this quotient, is less than n divided by k plus 1. One can check this easily. It is true for any real number. So instead of n divided by k, place alpha, a real number, and here alpha, and check on the real line axis that this is true. But here, the right hand side is just n, because here we have 0. So the total number of objects is less than n, which is a contradiction. Hence, there is a box containing at least the ceiling of n over k objects. Problem: what is the least number of area codes needed to guarantee that the 25 million phones in a state can be assigned distinct 10-digit telephone numbers? Assume that telephone numbers are of the form n, xx, nxx, xxx, n represents a digit from 2 to 9, x represents a digit from 0 to 9, and the first 3 digits here form the area code. Solution: the total number of objects are the 25 million customers' phones. 25 times 10 to the 6. The boxes are the different numbers that we can write with the last 6 digits in a phone number. And these are, here we have 8 choices, and then for each of the x's we have from 0 to 9 we have 10. So 10 to the 6 times 8. These are the number of boxes. Now apply the generalized pigeonhole principle. There will be a box containing the ceiling of 3.125, which is 4 objects. To distinguish between them, we need at least 4 area codes then. Problem: show that there are at least 6 people in California, population 37 million, with the same 3 initials who were born on the same day of the year, but not necessarily in the same year. Assume that everyone has 3 initials. So the number of objects is the set of people, so 37 million. And the number of boxes are the number of initials, 26 letters cubed, so 26 cubed times the number of days in the year, 366. The quotient of this is 5.7576. The ceiling is 6. And the pigeonhole principle applies, so we get the answer. The next problem, find the minimum number of objects such that at least R of these objects must be in one of k boxes when these objects are distributed among the boxes. Let's consider this number n, which is k times r minus 1 plus 1. Then the ceiling of n over k, this quotient from the generalized pigeonhole principle, is this. Now divide each term by k. K cancel out here. So you have r minus 1 plus 1 over k, the ceiling of this. Because r minus 1 is an integer and 1 over k is less than 1. This is just r. 1 over k is positive. So there is a box containing r objects. If we decrease this number by 1 and have k times r minus 1 objects, we can distribute these objects evenly into the boxes so that each of the k boxes contains r minus 1 objects. So the smallest number that satisfies the requirements in the problem is k times r minus 1 plus 1.